So they received their PhD at Rutgers, followed by postdocs at Wayne State University and Yale. So they are now a Ruff Fans Dean's Faculty Fellow at Vanderbilt University. More recently, they also received the DOE Early Career Award on topics very closely related to what they'll be talking about today. And they're also a co-PI on the NSF-funded Jetscape collaboration. So with that, I'll let you get started.
Okay. Yeah, thank you guys very much. Can you all hear me well? Okay, good. So the two things I need to apologize for. One is I won't be around to discuss a lot after the colloquium. I have to immediately run. I have a flight at 7 p.m. because tomorrow morning I become a U.S. citizen. So I have to be in the courthouse at Nashville. So I also have to say I was really looking forward to coming here in the spring, and then this happened. The eclipse was the day that I was supposed to give the colloquium, but then you can see that's my version of this. I was actually at Yale hanging out with some people. But yeah, so I always want to start off my talk by thanking the right people here. So these are my wonderful group members with the different collaborations and the different funding sources. So I want to give you all a story today, okay? So we go back to one of history's famous storytellers, and there seems to be that you need to have three parts to a successful story, right? Think Macbeth, think Star Wars, right? Same, or Lord of the Rings, same concept, right? You need harmatia, which is you need some kind of main character who has a tragic flaw in them, right? And you will then have some kind of eureka moment that feels like, oh my God, this is it, this is done now. But then you have this reversal. That is the thing that makes you realize, oh my God, maybe the true character flaw is in the, is in the character all along, and we didn't notice it, or something like that, right? That's the story. Hopefully we get there today, okay? So this is my talk. It's back to fundamental QCD. The story, the main characters, as you have guessed, are quarks and gluons, right? So let's introduce them. Let's find out what these guys are. So quarks and gluons are, at their foremost, fundamental particles, represented in the standard model as these three generations of quarks, the up, down, charm, strange, top, bottom. These are the three generations. The highest, the third generation is the ones that have the highest mass of the quarks. So the proton, for example, at rest is only made of the up, up, and down quark. The neutron is the down, down, and up quark. So that essentially comes on the first generation. At rest, okay, we come back to this later. You also have gluon here, which is the force carrier of this strong force, one of the four fundamental forces in the universe. So their interactions, their dynamics are described by a quantum theory that involves color, right? Color is a charge that is introduced in the theory to describe interactions between quarks and gluons, their couplings, their joint mesonic states, and so on. So what makes QCD unique compared to electrodynamics, for example, is two things. One is that the gluon, the force carrier, has color charge. So the electromagnetic force carrier, the photon, does not have electric charge, right? It's neutral. So the gluon has color charge, not just one charge, but it carries color and anti-color. So you can have a total of 8 different types of gluons, right? Another important feature is that the strength of the interactions that describe between quarks and gluons, the so-called coupling constant, is really not a constant, right? This x-axis here is a function of the energy at which you're probing the system. So the larger the energy, the smaller the scale with which you can see. The weaker the energy, the longer the scale, right? So at very low energies, you can see that the coupling constant, this alpha S, rises, and not just rises, it rises rapidly, right? So as you go to low and low values, this alpha s goes to values around 1. And when that happens, you can't perturbatively expand your calculations anymore. Because any term that includes alpha s or alpha s squared and alpha s cubed, they diverge, right? As you have a constant that has a value greater than 1. So this region is non-calculable from our current theoretical principles, right? That is the region of confinement and hadronization where you can't talk about quarks themselves. And every time I see this, I always realize this looks like BB-8 from Star Wars. You have a quark-anti-quark pair. That's basically the meson structure. You have quark-quark-quark connected together with strings. They are the gluons. Those are the baryons. So you get these confined states. Now, when you go to the other regime, that is very high energy, you can talk about these objects as if they are asymptotically free, right? This was the concept of asymptotic freedom, awarded with the Nobel Prize in 2004, where you can deal with individual quarks and gluons as individual objects. You can talk about their interactions in a scattering sense. They don't have to be confined in this structure anymore. So one way to do that was to increase the energy scale of your system, right? Here I have a bunch of hadrons confined. So I am from Nashville, Tennessee, which means it's still pretty warm outside there, even now, more warmer than here. So we could imagine putting it on the grill, right? And what happens when you put it on the grill? What's going to happen? You lose all the boundary, right? You heat up the system to a specific temperature where you have now lost the individual confinement. These are not asymptotically free quarks and gluons, but they are strongly coupled system that we call the quark-gluon plasma, right? So you could determine this by an equation of state. You could determine this by a specific shear viscosity. It flows like a fluid. It sounds like a fluid. It has properties of a fluid. Therefore, it probably is a duck, right? Which is a fluid in this case, going through water. So this is what we call our QCD phase transition. So you go back to your example that we all learned in school, where you have water, you have pressure and temperature in the phase diagram. As you increase the pressure, you reduce the temperature or increase the temperature, you end up in these different regions, water, ice, and steam, right? So here, the x-axis is baryon density. It's essentially the energy density that needed to create baryons, right? So technically, this is the baryon chemical potential. The y-axis here is the temperature of the system. So for reference, let's ground ourselves. The early universe is right over there, probably, right? Very low baryon density, but very high temperature, right? Because baryons haven't been created yet. We're talking a few microseconds after the Big Bang, right? Very high up. Now, on the other side of the axis, you find neutron stars. Very high baryon density because they're basically neutrons are baryons, right? All smushed together, high energy density, but very low temperature because you know that neutron stars are cold, right? This entire region that goes from the early universe till the neutron stars, that's what we call a quark-gluon plasma. There's a bit of an interesting discussion, which it's always fun over dinner or drinks, whether it is the quark-gluon plasma or a quark-gluon plasma. It's like you go to a restaurant and do you order the chicken soup or do you order a chicken soup, which is a specific recipe. So here, the prescription in order to create this quark-gluon plasma might be different in the different regimes, but the equation of state better be compatible with each of the systems. They should be able to transition from one state to another state, right? But in order to go from a confined system of hadron, like a hadron gas, where you could use your known equation of state, you can go from here to there. We expect to have a first order phase transition in this case. there's also a theoretical expectation of having a potential critical point, which is a second order phase transition where you reach criticality in your correlation length. And this is dotted because we don't know where it is. I mean, this is still a cartoon representation. It could be here, it could be there. We're not really sure if this second order correlation actually exists. So the goal of studying this, right, is to go to a system that existed, as I said, a few microseconds after the Big Bang. So some things happen here, inflation, we expand, and you get quarks and gluons, so there's this sort of transition region here, and then everything that happens over here, you see the cosmic microwave radiation, that's the last background that you see with your telescope. You have to go to another system to go beyond that, and we do this now in our lab where we create these little banks. So maybe look at this screen, which is the black is a little bit better. Just for this video, how do I turn it off or down? Okay. Is it this one? Third one says movie. Okay. All right, good. So to just put ourselves in the frame of watching this video, these are Lorentz contracted nuclei, right? Nuclei, in this case, a lead nucleus, which is pretty much a spherical object. It's traveling at, 0.99995 times the speed of light. So it is relativistic. So you have Lorentz contraction along the direction of motion. That's why it turns into a pancake. You have one pancake coming from here. You have another pancake coming from there. They are baryons. That's what you started with. The time frame. So this is Fermi seconds, right? Fermi seconds is in units of the speed of light. So this is how much second does it take for light to travel 1 Fermi, right? So speed of light, 3 times 10 to the 8. A Fermi is 10 to the minus 15 meters. So you convert to seconds, you get 10 to the minus 22 seconds. This is Yocto scale physics. Okay? That's the process in which this simulation runs right now. So they are about to collide. Let's say they collide at that point, and you end up with lots and lots and lots of particles being produced. You get different types of mesons. You also get some baryons. You get color creation with respect to strange. This simulation only included light quarks, but if you include heavy quarks in your simulation, you could get a lot of those mesons and baryons as well. But you can see this really expands as a fluid in this simulation, of course. This is a simulation that uses hydrodynamic code. So the question is, how to study this plasma? Okay, so feel free to stop me and ask me any questions as we are going. So you guys probably remember in 2020, like kind of second half of 2020, when you try to go to a restaurant, they would like shoot this at your face to find out if you're okay and then let you into the restaurant. If we do this to the plasma, it's not going to end very well, because that's what it's going to show you. That this is the hottest form of matter that we have created. This is a technical Guinness World Record that is held by CERN, first held by Brookhaven Lab across the water, and now held by CERN because they created a hotter plasma. But this is, a billion times hotter than this kind of the core of the sun, right? So this is very, very high energy. So ideally, what we would like to do, and I always like to say this as physicists, when in doubt, shoot a laser at it, right? Or when in doubt, fit a Gaussian, either of those. You'll probably get somewhere, right? If you do either of those. In this case, it would be really cool to shoot a laser at the plasma, but what's the problem, guys? This damn thing exists only for 10 to the minus 22 seconds, and the best we currently can do is attosecond laser pulses. So this is the Nobel Prize last year to these 3 wonderful people. So our physics process is Yocto scale. So we are still 5 orders of magnitude off from timing a laser pulse to interact with our system. That's not going to happen. So what we do is actually use the particles that come out of this to study itself, right? So we're going to look at the particle distribution and then compare to some expectation or some calculation, okay? I want to do a short detour. So there are quite a few detours in my talk, and I think it's relevant for a very broad audience, is that heavy ion physics, this part of high energy nuclear physics, is really a very interesting subfield, right? Because it is a marriage of thermodynamics. You have high density, high temperature, black body spectrum. You have statistical physics because you're dealing with a sort of a grand macro ensemble here that particles are produced, right? You could also model the heavy ion system as sort of the expansion of these ultra cold lithium atoms in a trap. This is a very, very cool comparison, and this is actually a few years old now, but let's say you're colliding these two nuclei, the overlap is relatively small, so you get this almond-like shape when the nucleus goes through. So imagine they are not directly head-on, but slightly shifted, right? So this almond shape is a spatial anisotropy, but because you are now constraining your nucleus, you made it flat, right? Which means if you go to the momentum space, so this is in position space, this is in momentum space, you get a different flattening, right, in the momentum space and anisotropy. So this transition from a spatial anisotropy to a momentum anisotropy is a fluid behavior indication, right? This tells you that your system remembers the pressure differentials that existed early in time followed through to the particle distribution, right? So you can compare now, if you create this almond at RHIC or the LHC, these are time in Fermi seconds as always. You go down, you find that you see the same behavior that you can actually see if you trap ultra cold lithium atoms and you let it evolve, right? If you put it in this very narrow structure, and this is at some time limit, 100 microseconds, and you go to 2000 microseconds, you see that they have spread, right? So two ways in which you can directly compare these two systems. So the rest of my talk will essentially be telling you how we can study this, what do we actually learn. So in the world of nuclear physics, we have this long-range plan in the sort of funded by the National Academy of Sciences and endorsed by the Department of Energy, the National Science Foundation, right? So this is our 2023 long-range plan for nuclear science. We call it the new era of discovery. And the recommendation 1 is the highest priority is to capitalize on the opportunities of discovery made possible by investments that we currently have, which is RHIC physics, right? How do we get there? There's also RHIC, completing the RHIC scientific program and going towards the next generation that I'll come to at the end of the talk, and also trying to understand what makes up the proton. What is the inner structure? Is it all quarks and gluons? Is it mainly only gluons in some scale? Okay, so let's put like some kind of time axis here and understand what's happening. So at time t not equal to 0, a little bit less, you have the collision just about to happen. At t equal to 0, say you have a hard collision, you get particles that are produced in the collision. Some of these are jets. They are high energy momentum exchanges between the individual quarks or gluons. You'll see an explanation later. And the quark-gluon plasma is formed a very short amount of time later because this is a fluid structure, right? In order to have a fluid, you need to have a pre-equilibrium phase. So there needs to be some time development that you allow for the system to get to an equilibrated phase and then behaves like a fluid, right? That's this delta T. Right now, this is not coming from experiment. This is coming from a model. So we could have some differences on that. So after this, we really have to understand why jets are cool, right? So for that, I have another detour. Jets are how we know there are quarks and gluons. right? So I really, really love this paper from Mary Gaillard and collaborators in 1976. So for all the students, highly recommend you read that paper. And she uses this word metamorphosis of quarks coming out, the collection of hadrons resulting from the metamorphosis of partons due to fragmentation and hadronization, right? Because in nature, you don't see quarks by themselves or gluons by themselves. They always come in this color-neutral collection of particles. So this transition, so if you measure this, you can then go back and infer that it came from a quark or a gluon. So a slight short note, there is this wonderful book by Mary Gaillard. Is essentially her life story in physics. She was the first female tenured faculty in physics in Berkeley. So highly recommend taking a look at that. You kind of see the history of QCD kind of develop in front of you. It's really cool. So this is an event display of a collision of electrons and positrons from the Tasso experiment in Germany in 1979. So what you see here is a characteristic three-jet event. You have electron-positron colliding, particle colliding with an antiparticle, which means they collide and create pure energy, right? Matter and antimatter, when they touch each other, they annihilate each other, right? From that energy, Einstein told us that energy can be converted to mass. So we can convert this E plus E minus into a quark and an antiquark. And one of those guys radiated a gluon. Each of these individual partons now forms this characteristic three-jet event, and because this was done in Germany, they called it the Mercedes event, because they love their cars, sort of obvious. So the energy scale you can see here, you have a 8.4 GeV, which is giga electron volts. For reference, 1 GeV is the proton mass at rest, right? You have 3 tracks that come here, and you have 4. You have one that has 5 tracks, 5.4 GeV, 3 tracks, 4.4 GeV. Now the question, which one is the gluon? Is it 9 o'clock? Is it 2 o'clock? Or 5 o'clock? Who says 9 o'clock is the gluon? No one. Very good. You're all very smart. Who says 2 o'clock is the gluon? Okay. So all the particle people are saying, or at least some of them. Who says it's the 5 o'clock one? Yeah. So good job. It's either the 2 o'clock or the 5 o'clock. I don't know the answer myself. When this was released by Daisy, there was a press conference, and a journalist asked this exact same question to the physicists who were presenting this at the press conference, and they did not expect this question at all. Yes?
How do you distinguish between the different jets? Like how do you distinguish quark?
So the gluon was radiated by one of those quarks, right? A quark or an antiquark, which means originally it was a quark and an antiquark. So momentum has to be conserved, right? So if you have 8 GeV, 8.5 GeV going this direction, on that direction I need to have a summed 8.5 GeV going around, right? Which means this one cannot be the gluon, right? So this is either the quark or the antiquark, which means one of these guys has to be the gluon. Now typically it's the lower energy one, but then gluons also create more particles, which could be it's that one or this one. Hard to tell. We don't know. Okay? Good. So now we have come to the tragic flaw of our main character. Quarks and gluons have color charge. They radiate, right? But it is essentially a probabilistic parton shower, which means, I like this statement a lot, different jets are different. They have different topologies. They have different structure. They have different particle production, right? So that's the first part. Once we have our jet being formed, it goes through the plasma. The jet and the plasma are evolving concurrently, right? The jets are made of quarks and gluons. The quark-gluon plasma is made of quarks and gluons. Therefore, they can talk to each other. They can influence each other, right? So any modification that we see in our measurement to our jet properties, and we compare it to a system that does not have the plasma, right? Then you can infer that these modifications are due to your plasma interfering with the jet evolution, right? So you make an inference in this case. So this is where we go back to what we expected. So this is a paper from James Bjorken, unpublished, Fermilab note, 1982, that says that if you have a jet, it might lose tenths of GeV of its initial transverse momentum while plowing through the quark-gluon plasma produced in its local environment. Now, this paper is the most highly cited paper in our field. It is also unpublished. It is also wrong. There is a calculation error in this. Bjorken missed a factor of 16 in the code. In the calculation, not in the code. So this is a good learning experience for all the students. I mean, it's okay to be wrong. You might end up creating a new field and having the most cited paper in that field, right? So if we talk about what specific reason leads to this particular type of energy loss in the plasma, you can have many different types, right? This is really the kind of structure of our field now, especially high energy nuclear, is that there are many, many different types of energy loss. These are all review papers from a few years ago. You can have perturbative QCD like radiation, kind of similar to the Landau-Pomeranchuk-Migdal effect. You can have medium-induced scatterings like kind of quasi-particle elastic and inelastic scattering. You can have viscosity effects where the jet feels the drag from the plasma as it's going through it, right? Because it is a fluid. You can have color decoherence effects, which we'll come to later. But really, in order to study what are the properties of the medium, this is a two-step process. First, you need to understand how your jets are modified. For that, you need to understand your baseline. What did you start with? How is it modified? Then you go to your theorists and you say, okay, this is the modification. What type of modification can give me this? What type of interaction between the jet and the plasma can give me this? Okay? So this was mentioned in the 2015 long-range plan of nuclear science. This is when I was a PhD student. And last year, I contributed to making this cartoon that went into the long-range plan 2023 is jets studying their jet medium-induced cascade of gluons is a key feature of probing the emergent properties of this plasma. What are its transport properties? How opaque is it to quarks and gluons, right? Okay, so that brings us to the second part, right? Once you have modification, you can directly compare to models and say where that modification comes from. What type of energy loss can give you this? What are the properties of the plasma that can give you this? So that was a relatively long introduction. The other two will be relatively quick, so don't worry. We go into Act 2 now. What are the properties of our jets? And how are they modified? So what do we want to measure, right? So from a theorist sort of perspective, right? Okay, this is an experimentalist thinking this is what the theorist thinks. It doesn't have to be that way. But they think that there is some perturbative structure that you can calculate using Deglab splitting functions, quark radiating a gluon, maybe gluon radiates more gluons. There is a prescription that you can follow for this, right? You follow that. There's something that you cannot deal with, that is the hadronization. You throw it into some lockbox, you do a little magic spell, you get particles that come out of it. Now, experimentally, what we can do is look at all the particles, work on a jet reconstruction procedure that has a specific algorithm, right, that takes you from your particles, recreates this sort of clustering tree, And the idea behind this theory experiment correspondence is that you can start to say that this splitting in my clustering tree is sort of like the partonic structure, right? This we have measured, that this splitting function looks very similar to that guy, right? You can follow along these splits and create the so-called Lund plane, which you have experts here, so I won't say more about that. And you can pinpoint what part of perturbative QCD fits that description and what part does not, right? So in terms of energy loss, I want to tell you something very fundamental, right? So the first things to do is to compare jets in heavy ion collisions to jets in proton-proton collisions. Proton-proton collision is, by definition, one nucleon on one nucleon. When I collide lead nucleus with a lead nucleus, I can have up to 700 nucleon on nucleon collisions, depending on the overlap, right? If the overlap is full, then every single nucleon can interact with each other. So if I want to think of a heavy ion collision as just a superposition of multiple proton-proton collision, right? It's just a simple test, no emergent phenomena, no additional properties due to the fact that you did have a plasma in there. This ratio of heavy ion collisions divided by a scaled proton-proton collision should be 1, right? And it is 1 for photons, for Z bosons. W's almost 1, but there's an interesting reason why it's not 1. We'll get to it later. But Z's and photons, they're electroweak. They don't talk to the plasma. They don't lose energy in the plasma. So when you make this ratio, you know that they are 1. So that's your baseline, right? When you do this for the jet spectrum, the production cross-section, you get a ratio that's less than 1. We call this ratio the RAA, or the nuclear modification factor. And essentially, it's you have a spectra in PP, and if I shift this spectrum to the left, I am creating a suppression in the ratio, right? Or I could just move the spectra down. Both of these could give you a ratio less than 1, okay? So now we can ask one question. Is jet energy loss dependent on the angle of the jet? Now, this is kind of an intuitive question, right? Let's say you're swimming in water, right? And someone asked you to carry a big plank on your back that extends your size, and you try to swim on it. The size that you have will be impeded by the water that you interact with. That will slow you down. So there is an expectation that wider the angle of jets, the more they will be suppressed. The physics reason behind this is you have the phenomena of a coherence length of the plasma. So if I have a quark that radiates a gluon, and the angle of this radiation is smaller than the coherence length of the plasma cannot resolve this particular radiation. It sees all of them as a single color charge. It sees it just as its mother, right? Because if you have a scale and the lines that you have in your ruler are this big, I cannot make a difference between, different lines in this chair, right? They will all look like one object to me. But if I have a very, very fine-tooth laser-defined comb, right, then I can distinguish them. Once I can distinguish the two individual objects, each of those will lose energy independently, right? So they become independent radiators, and this energy loss, after you account for interference and stuff, there's a little bit of a technical calculation in here that goes in, and it says that this energy loss is large, right? So you can ask the plasma, you can be an eye doctor, and you can ask it, how many gluons do you see? Do you see 1, 2, or 3? The more gluons you see, the more energy loss happens. So this is where I come to the next detour that I'm very excited about, is how do we quantify the scale dependence? Because this is a scale, right? This is a resolution length in the plasma. So for that, we go back to our friends from cosmology who have told us that if you want to quantify a scale-dependent structure, you look at correlations. You look at 2-point correlations or 3-point correlations. They tell you something interesting about the system. They tell you about the fundamental resolution structure in your thing that you're studying. So if you go to the cosmic microwave background, you can look at the endpoint correlators. They give you all the different modes of the system, right? In heavy ion collisions, the hope is that if my jet goes through this block of plasma, now in reality this should have been a fireball because it's a hot object. But the graphics involved to put a fireball and then a jet behind it was not great. So we put it like an ice cube, sort of ironic way, right? So if you have some material interactions with the plasma for your jet, the hope is then that their scale dependence is imprinted on the structure of the jet, right? So that's the fundamental point here. So this is where we define our energy correlator. And there's been a flurry of work in the last few years. This was originally proposed by Maldacena and collaborators in 2008. And also, even before that, there have been people looking at it. But now there's sort of this resurgence in this field. So you basically look at pairs, particle pairs within your jet, right? You calculate their delta R, which is their distance between each other. And then you weight that distance by the product of their energies. Why do you want to do this? What is the physics that you learn here, right? When you have large distances, this distribution looks like a falling distribution. And you can calculate this in theory without using any hadronization correction. Pure perturbative QCD, you can calculate this. The slope of this quantity is sensitive to your alpha S. There's been a measurement in CMS that extracts this. Alice is trying to do this as well. But you can get physics out of the large angle structure. Now, if you just want to say, if I throw random particles, no correlations at all, right? I just throw my dice, I get a random particle here, I put a random particle there, a pure thermal fluctuation. I calculate what this quantity looks like. It is just a function of distance, right? It's just the Jacobian of finding two particles close together in a space. You convert it to a circle. This is just a rising trend that you have. So if you have no inherent correlations, this quantity is a positive slope object. If you have physics, it is a negative slope object. Reality, you have both. So when you have an observable that has a negative slope and then a positive slope, you can apply mean value theorem. There has to be a transition somewhere, right? So for a realistic jet, this is what we see, right? What is very interesting is that this peak structure depends on the scale of the jet. And it is essentially inversely proportional to the jet PT times lambda QCD, which is the fundamental scale involved in QCD, right? So as I increase my jet energy, the peak of this transition region becomes at smaller and smaller angles. Now, the reason why this has many different labels is that we can't, as a community, we each like to call the same thing different ways, right? So CMS calls it delta R, other experiment called delta capital R, other experiments call it RL, it's the same thing, okay? So when you scale this x-axis by the average PT, now remember the peak is lambda QCD divided by jet PT. So now if I scale this jet PT over there, they all line up together, indicating a sort of universality, right? Don't take my word for this. Take this. This is a comparison of data from STAR. So jets, 30 GeV jets, all the way up to CMS through Alice. So 20 to 40, 30 to 50, 60 to 80, 1.5 TeV. So 2 orders of magnitude. Tens of GeV to thousands of GeV, right? You scale it, and they're roughly similar. Okay, there are some differences, obviously, that we can see. There's quark-gluon differences between each of these quantities, but overall, I mean, this is crazy. For 2 orders of magnitude, all these things lining up in a roughly similar space, you can say that we don't have the correct resolution here, and this is also not lambda QCD. It's not. It's something times lambda QCD. We are working to figure out what that thing is, and it's kind of complicated, but overall, this seems relatively universal. So now I can show you what we did in CMS is the red marker here is the lead-lead data. The black marker is the proton-proton data. So we expect energy loss and modification in the red points, okay? So we compared it at the same jet energy of both of them, and you see that this distribution is shifted to the left. So the red marker, the peak, seems to be shifted to the left, and the PP, you see an enhancement. You see this modification of your shape at larger angles. And what this is something that we call survival bias in heavy ion collisions. So if I go back to this thing, if I have energy loss and I compare at fixed energy, right? I fix my jet energy here. I compare lead-lead and PP. The lead-lead jets to end up in that PT range lost some energy. So if I compare 100 GeV across both of those samples, that's not an apples-to-apples comparison because the lead-lead sample ended up at 100, but it started out as 120 because it lost energy, then ended up as 100 in your measurement, right? So we can now go back, use this peak structure, and then say that if I compare lead-lead 0 to 10 to PP 140 to 160, 20 GeV higher, you can see that they exactly match in this region of universal transition, right? This means that we have identified a subsample of jets that have the same initial virtuality. So I'm throwing this word out. You can just take it as energy, but it's the more technical term is virtuality here. So we now have evidence that all the jet measurements that we did in heavy ion collisions the last 2 decades, most of them were comparing apples to oranges. This is where we are now, right? We have now evidence that we can compare now at fixed apples and oranges. Now, this did not make it into the paper. This will come in the next paper. But for now, we still compare apples to oranges, but just note that this region can be flat. It can move down a little bit. But you see this enhancement, and this enhancement, this change in shape happens at a particular angle, right? So this is what we call angle-dependent energy loss, and the prediction from different models can actually tell us what is going on here, right? So the next slide, I'm going to show you, so these are true predictions. The theorists did not see the data before we showed it in a conference after comparing all of it. These are 4 different models. You have linearized Boltzmann transport. This is sort of a hydrodynamic model. This is a hybrid ADS CFT that has strong coupling, kind of energy loss. This completely fails. This one sort of gets close, but it's not there. This is a model of perturbative QCD, but weak coupling. And it fits the data where jets went through a strongly coupled medium. This is Broncos. This should not happen, but it does. Okay? We also have a pure theoretical calculation by Jack Holguin, Carlota Anders, and collaborators. This is a calculation based on quarks and gluons. There are no hadrons here. And the fact that they match the data in this region with the inclusion of color coherence that enables, you can see these different kappa values, they tell you how much energy loss you have. You can extract the impact of color coherence from this data, right? So you can find out not just what happened to your jets, but how it happened to your jets, right? Okay, so that comes to the last part, is that this is actually very useful. Once we know how jet quenching is dependent on the character of your jet, how the jet quenching is dependent on the structure, the topology of your jet, you can find out that different jets are quenched differently. This is a very useful thing for us to know, right? Because if you look at your jets in the energy loss version, their shower evolution is probabilistic. Energy loss is probabilistic. Hadronization is probabilistic or stochastic. I would be sad if it's completely random, but such is nature. So in order to understand what happens to your jet, you have to remove at least one of these terms. You have to remove at least one of these probability distribution. Once you fix those, then you can go to your jet and ask, what happened to you in the plasma? And therefore, you can ask, what are the properties of the plasma that interacted with that guy? Okay? Good. So that's exactly what we are doing now. So we, as part of this Jetscape framework, this was shown in the long-range plan. This is an extraction of the shear. This is the bulk viscosity. This is the shear viscosity using Bayesian analysis with all the data that we currently have. This is part of the NSF-funded Jetscape framework. I'm not going to go into this. This is just all the data that we use for our Bayesian fitting, right? And this goes in and we can extract Q hat, which is the kind of stopping power of the plasma, right? Q hat is how much energy lost to the medium per Fermi traveled in the medium, right? So this is Q hat as a function of temperature, you see here. And because the plasma is expanding and cooling down, your Q hat comes smaller and smaller. So you lose less energy as you're evolving in your medium. So this, you can find all the information on the Jetscape website. So in the last 5 minutes, I just want to highlight what are we doing next. So I want to focus on what we are doing at RHIC. This is the photo that I took on the plane coming over here. And this is sPHENIX right here in this space. So sPHENIX is the new detector endorsed by the long-range plan. We built it. It's taking data. It took data last year. It's taking data right now. The priority for the sPHENIX physics program can split up into 4 pillars. We have jet substructure, looking at QCD phenomena discovered at RHIC. There's also the capability of varying the different flavor of the quarks, right? We can look at bound states and also some cold QCD physics. This is a picture of data taking this year, but you can see a lot of very young, excited people there. This is the sPHENIX detector. It's really a standard multi-purpose onion detector, right? You have many, many, many layers. Each layer performs a specific role, and you can study particles that are produced from there. I just want to flash this because this is work done by my postdoc, Ben Kimmelman, from data taken last year, run 23. This was very recently approved a preliminary figure. This is the energy density for different overlap regions. So 0 to 10 means you have very strong overlap. This is the energy density that we generate in our calorimeters. This is data that we actually measure. When you have a weak overlap, you see that you get very small energy density. This is just a function of how much interaction you have. This is sort of an estimation of how violent your collisions are, right? And this has a characteristic, I mean, you can call it a horseback, or you can call it like one of those, what is that giant dinosaur, the lost in time over, the big neck guy. It could be that dinosaur as well. I mean, it's one of those very characteristic shapes. This is data from this year. This was taken with an event that was taken in June of 2024. You can see data from each of the different calorimeter systems. This is proton-proton collisions. So you see one jet over here. You see another jet that's actually split into 2 because this is gluon radiation. You remember I showed you quark, antiquark, and gluon? That's exactly what is happening here, but in proton-proton collisions. This 40 GeV jet comes from a 100 GeV beam, right? So if you now go to your parton momentum fraction, 40 divided by 100, that's 0.4, you are in the valence quark regime. This is a quark. That also could be another quark, not an antiquark because you're not conserving energy density here, color. So you can also look at the delta phi. You find that they're mostly back-to-back with some interesting structures here. This is just to show that our detector works. We're taking data. Everything looks very cool. All right, so the last thing, if you just go to Inspire and you plot the publications that has the word jet and quark-gluon plasma, this is a very good fit. Which means that by 2050, we're going to have 10,000 publications a day. It's just going to happen, right? That's why I need all of you to start working on it as well. So the recommendation from the long-range plan is that we construct the Electron Ion Collider as the highest priority for nuclear physics in the US. So here's the prescription of the EIC. It's going to replace RHIC at Brookhaven. We will add an electron ring. One detector is promised by the US funding agency. They only promise a cartoon of another detector, not a real detector. But this one will, hopefully we will get it too at some point. Because what's physics with only one detector? I mean, you need two, right? So this detector, we call it the EPIC detector. We love our names. Electron Proton Ion Collider. It's a very sad acronym. We could have gone and named it Athena. I mean, can you imagine? Some people voting against Athena. I don't understand why. But this is another detector that has multi-purpose. It has particle identification. EIC is and will be a discovery machine. What we learn from the EIC will fundamentally change our understanding of nuclear structure, of properties of the proton. The scattering that we have from the electron will give us very precise dynamics to essentially scan the nuclear structure to see what's inside the proton, identify gluon saturation, and so on. So in order to get work for the EIC, this is a program I started in Vanderbilt. Actually, technically I started it at Yale, but then we expanded it at Vanderbilt. There's a Scientific American article I wrote, is that high school students now are the future grad students that I will hire for the EIC, or the future postdocs that I will hire for the EIC, right? Or the future colleagues who will work with me. So we did this high school workshop where high schoolers in the Metro Nashville School District simulated EIC collisions on their machines. You can go to this link. It's also, you can find it from my website. This program is fully public. You can take it, anyone can run it. You can run the simulation on your phone right now. You go, it opens up a Jupyter binder notebook, and you can import Pythia, which is the Monte Carlo generator, run your analysis, and the students really enjoyed having a fun time. And this is one of the students who worked with me last year, presenting her work, correlating charmed and light mesons in electron-proton scattering. I'm very sorry to contributing to the arms race of students, but this is very exciting. So that brings me to my last slide. The era of precision jet substrate is here. We can go to non-perturbative dynamics. And lastly, the scale structure is imprinted, and we will show it. So that's all. Thank you very much. All right, I have 15 minutes before I run away.
Thank you very much. Let's see if there are any questions.
Yeah.
Sorry, I'm not an, nice talk, by the way, very nice presentation. I'm not an expert, so it's just a clarification question. So
Sounds
could
good.
you repeat why the energy-energy correlation increases at low values of delta R?
At small angles?
Yeah, small angles. You were talking about random, totally random.
Yeah, if you just do completely random particles, right, the distance between two particles is just a function of density of particles. And that scales as a function of the circumference, so 2 pi r.
Okay, yeah.
That's all.
Thanks.
Yeah. Mm-hmm.
Great. Any other questions? I have maybe a question while people are thinking, but
Yeah,
feel
sure.
free to raise your hands. If you could go back to the slide with all the theory predictions on there. Yes, this one. Could you maybe repeat what you were saying about the prediction from Jack here, and
Yes.
and maybe like also clarify what the implications would be if this were a correct model here?
Yeah. So Jack's calculations, so this is Jack Holguin, is a perturbative model with a very dummy non-perturbative correction so that you get a hump, right? That's why it doesn't match in this region. So what we did is to normalize the data, normalize the calculation to the data such that in the region where the model distinguishes, we don't compare to data before the normalization, right? So in the region where all their calculations agree, we normalize that to the data in this green region, and then we plot the distribution. So the reason why we don't normalize the entire region, which is what you do in the correlators, is because their model is very rudimentary for the non-perturbative structure. So you're going to you need to find a region where you do the normalization, right? So the implication for me is that this model seems to imply that including coherence-dependent energy loss is a significant factor in modifying this observable. So what would be very cool is to take this coherence model, sit it on top of this hybrid with the wake description, and that would be a more realistic quantity, right? But even then, you can compare to Jewel here, which includes only elastic scattering. There is some deviation with the data. I mean, it is sort of precise. You see some differences in this region that is sort of interest here. So I think what we are learning with these two-particle energy correlators is that there is interesting physics. We probably need to go to three-particle correlator to tease it out. Yeah.
Great.
A very nice talk. I want to look at your last slides. You indicate that you can learn something about perturbative versus non-perturbative QCD. What can you learn things that people could not do based on PP scattering?
What can you learn?
That cannot be learned based on PP.
With the Electron Ion Collider. Yeah, so PP scattering is very useful. I mean, it has shown us so many things, right? But the problem is there are, at least one example of a problem is you have a relatively messy environment, right? Because you have not just one of the hard partons interacting, you would have to look at all the other interactions. So if I take a particle from a jet, it's not guaranteed that that particle came as a consequence of the parton shower. It could have come from something else, right? Because you have a dijet system, this gluon could radiate, that gluon could radiate further in. You have these non-global contributions, you have multi-parton interactions. When you do electron-ion collisions, the electron emits a virtual photon, that photon interacts with your quark, and every single particle that you measure is associated with that quark's fragmentation. Once you measure the scattered electron, it's gone, right? So you can very clearly measure fragmentation function to high accuracy and high precision. Yeah, that would be a dream. Identified fragmentation function, that would be amazing.
Hi. So I have a similar question, I think, to the last one, but I've just been sitting here thinking about the slide. Could you put Jack's and Carlotta's prediction back up? So, I mean, this is amazing, right?
Yeah.
The story of substructure in heavy ions has been going on for a long time, and I think this is one of the most convincing comparisons. This is the first one. Of,
the first one
prediction like this to data.
A fully perturbative calculation.
Yeah.
On top of data. Okay, I mean.
This is a big milestone, right?
You have to ignore all this stuff, but yeah.
Sure. But in the region where it's supposed to work, it seems
correct.
To. So, you, I think, made a pretty convincing case that we're starting to understand better than we have before what's really going on, right, in medium with jet evolution. So my question is, because you have perspective that I don't on the heavy ion side of things, can we start answering bigger questions now? Like, where is this going in the high energy at the LHC heavy ion program?
Yeah, so there's really, I think, two things I want to answer for that. So first thing is the energy loss at the LHC is very wide, right? The medium is different. It's at a higher temperature. And therefore, the evolution of the energy loss goes out to very large angles. So we essentially stopped at R equals 0.4 because we needed a result. It would have taken another year to get to a larger angle. And yeah, we need to do this soon. But we will do this for the larger angle. So this is not the full recovery of the energy loss, right? I think you need to have that if you want to make a clear picture of this is how I lost the energy, this is where that energy is. That tells you something about the diffusion property of the medium, which this does not, right? So if you go to RHIC, the energy loss at RHIC is smaller. You can recover all the energy at RHIC at 0.5. So that's why I think measuring this in sPHENIX would be very cool, is that not only would you see a rise, you would see a dip after that. That we have never seen anywhere. So you can fit two parameters to your model. One is the impact of coherence. When does it turn on? When do you recover the energy? That will conclusively tell me what has happened to this jet. Yeah.
Cool. Good. I look forward to it.
Any last quick questions? Doesn't look like. So yeah, let's thank Rithya again.
Thank you very much.